This is the best of the Rotary E-Club of Silicon Valley, where we select from our library of hundreds of past presentations. One of our goals is to connect with people who have wonderfully interesting stories that inspire us to think about solutions to vexing problems in all sorts of ways. We hope you will find inspiration in what you hear today.
The problem is that wind and solar, although their prices come down extraordinarily, and that's great, we are faced with the inexorable challenge of matching Mother Nature's supply curve to civilization's demand curve. We're taking idle oil and gas infrastructure and turning it into the lowest cost, most flexible energy storage in the world.
Welcome, everybody. This is the Rotary E-Club of Silicon Valley, and every week we work to bring you stories of people who are making a difference in the lives of others, improving their communities locally, globally, and digitally. And today we're going to talk energy. So our speaker today is Kemp Gregory, the CEO and co-founder of Renewell Energy. And when we talk about issues related to energy, there are a number of questions that often don't get enough attention, and these guys have come up with a beautiful way of addressing one of them. And so we're quite excited to get that story. So Kemp, with that, I hand the mic over to you. Welcome to the Rotary E-Club of Silicon Valley.
Great. Thanks very much. Nice to be here. I am excited to talk about what Renewell, my early stage startup, is up to. All right. So what I'm going to talk today to y'all about is converting idle wells into gravity-based energy storage. The concept of a battery continues to expand as all sorts of different technologies are coming into the battery world. We are an entrant into the battery world, except we are strictly mechanical. So I'll explain the system in full detail later, but really there's a lot of poetic justice here in that what we're doing is we're taking idle oil and gas infrastructure, which is worth, like, not an exaggeration to say trillions of dollars, and turning it into an infrastructure that's going to help us build the future. So a little bit about myself, how I got to this position. I'm originally from Houston, Texas. I went to UT Austin for mechanical engineering. Then I went to go work for Shell as a completions engineer for 5 years. So I was a petroleum engineer in West Texas, Canada, and Argentina. And I was actually living in Argentina working for Shell. And I decided I don't want to work for Shell anymore. I don't want to work in the oil and gas industry anymore. I want to do something else. I want to go into the electricity side of things. So then I went to Stanford to get a master's in civil environmental engineering. And that's where this idea was born. It was sort of a divine combination of everything that I was at Stanford to learn, plus a lot of the things that I learned from my years at Shell. Okay, without further ado, let's talk about the problem. Okay, the problem is that the idle well count in the United States and Canada is enormous. It's 2.6 million wells, the vast majority of which are in the United States. And it is an expensive and slow process. It would take about 100 years to clean them all up in a business as usual scenario, 182 billion. And we're going to leak a lot of methane in the process if we keep doing what we're doing. So really, we're here to talk about two problems, actually. The other problem is that wind and solar, although their prices come down extraordinarily, and that's great for lots of reasons, we are faced with the inexorable challenge of matching Mother Nature's supply curve to civilization's demand curve. Neither are willing to budge. So what we've got to do is create some energy storage that can move things around, specifically move supply. And so that, as a society, we have turned to the lithium-ion battery, which has been very, very useful, but it faces some challenges in doing this, solving this problem at scale. Those problems are, it's high cost. It's usually only applied for short duration. And by that, I mean, tops out at the 4 to 8 hour range, but we're going to need some more like 50 hours worth of coverage in certain scenarios. It degrades over time, and there's an environmental impact, all of which I'll touch on a little bit later. So the way we solve the first problem is called plug and abandonment. It means that the well goes from being a liability to being nothing. But a little bit of context is key here. So when I talk about an idle well, I'm talking about something that has 3 distinct characteristics. It is not plugged, so it's just sitting there open to the reservoir. It is not an orphan well, so it is still owned by someone, usually a big company, and it has not produced oil and gas in the last 2 years. So it's sitting there truly just doing nothing. And they're often on top of depleted reservoirs. So even if oil price went $500 per barrel tomorrow, it's not like all the idle wells would just go away. We're talking about a relatively permanent liability. But every oil and gas company is required to clean up every single well they own. And that's where the plug and abandonment comes in. And I'm going to walk you through what that process looks like quickly. So you take the pump jack away, you take the electrical infrastructure away, you take the tubing out of the well, you put 3 plugs in it. If we're in California, other states have different rulings, but it's typically about this. You cut the wellhead off and you make it whatever it was. Forest if it was forest, desert if it was desert. The thing is, that's expensive. On average, 70 grand and can be way higher, up to 5 times higher than that. Well, there are averages that are up to 5 times higher than that. There are wells that cost $1 million to plug and abandon. All that said, about 20,000 happen every year, but it's not something the oil and gas company industry is really that excited about. They don't want to do it because it costs money and they don't make any money in the process. So the other solution that we've turned to for the other problem, the renewable energy problem, is lithium-ion batteries. So here's some stack ups of various battery technologies and their 2030 capital cost. And here's how we compare against them.
Slide 5 shows lithium-ion batteries capital costs ranging from $145 to $250 per kilowatt hour, and gravity wells capital costs at only $5 per kilowatt hour, more than 90% cheaper.
So we can have extraordinarily low capital costs for 2 reasons. 1, we're repurposing a bunch of infrastructure, so we don't have to pay for that much. And 2, we actually have 2 revenue streams. 1, there's the energy storage services that we provide to the grid, like any other battery. And then there's another one where we are helping the oil and gas company convert their idle wells into gravity wells, and we charge them for that. That's service. And so in doing so, that well gets to get pulled off of death row, if you will, and given a whole new life. Okay, so for every time that we, extract more lithium out of the ground, at least in the hard rock example, we're talking about a massive mine versus an oil well cleanup, the price of lithium carbonate has gone up 7 times over the last 2 years. It's gone up by 7 times over the last 2 years. Versus us, we'll just use waste streams, used oil field tubing and sand. Lithium-ion batteries degrade up to 40% over a 20-year lifetime, whereas we have zero degradation because we're strictly a mechanical system. So without further ado, I'm going to tell you a little bit more about how our system works. So the better solution to both of those problems is energy storage plus plug and monitor. So we're going to increase the environmental compliance and create the most flexible energy storage in the world. So we start by taking the pump jack away, leave the electrical infrastructure because that's super important, take the tubing out, put a plug in the well, and now we install our system. So we call this system a gravity well. It is a mechatronic energy conversion, or just another way to say a fancy regenerative winch. It has a motor generator, kind of like a Tesla has a motor generator. So when the weight is moving down the well, we're pushing power to the grid. And when the weight is moving up the well, we're pulling power from the grid to motor. So it's weight moving up means we're motoring. Weight moving down means we're generating. So it's power in, power out. So just to reiterate, totally mechanical system. It just works by converting potential energy to kinetic energy to electrical energy. Okay, so how it works, a well needs to be deemed suitable. All right, so it's going to meet 9 criteria for whether or not the well is a good candidate for conversion into a gravity well. So let's say that this well on the left here has passed all the tests. It meets all the criteria. So what would happen is a workover rig, which is like a shrunken drilling rig, would go out and do the first few steps of plug and abandonment. The same steps we just walked through, actually. So the pump jack goes away and the tubing gets taken out and the plug gets set at the bottom of the well. And then we use that same workover rig, the shrunken drilling rig, to install our weights. And then we set our system down next to it and it's ready to go. So what's happening there is that finally, it'll serve for 30 years as an energy storage mechanism. So performing things like load shifting, electricity arbitrage, and frequency regulation. Lots of things that other batteries do. Then I'll get to sort of the unique application of our battery in just a few slides. So we field tested this. We did it in Texas. There's a beautiful well that we found in Texas and then repurposed. And we're going to get to see a few videos and images of that.
A full video of this presentation, including all these slides and images, is available on our website, Rotary.cool, and on YouTube. Links are in the podcast notes.
There's the workover rig. There's us moving in our prototype, which we call Artemis Prime. And here it is operating. So a little tour, you can see briefly that the drum is spinning counterclockwise, which means we're pushing power to the grid, or we're in that generating mode, which means the weight is moving down the well. Then we packed it up and we shipped it out to California. So here's us in a field owned by Renewell Energy. So we picked up the system, set it down, and now it's operating in California. The reason being is that I think California is the beachhead market. Lots of good things going on in California for this process. So technology advantages, just a little bit of summary and some more information. So I mentioned how we seal the wells. So the well won't leak any more methane. Even if it does, we would be able to monitor it and know. So in that effect, what we've essentially created is a net negative CO2 equivalent energy storage technology. We will stop more methane from leaking out of the well in its CO2 equivalent quantity than is the equivalent amount of energy and its CO2 equivalent emissions required to build the device. So like the embodied carbon versus the amount of carbon we're going to prevent from hitting the atmosphere in the form of methane, this is significantly more. So for every device, we're actually reducing the amount of CO2 and not adding. What we've done that's truly innovative is combine gravity-based energy storage in a distributed energy resource. So that's DER. And what we've done is we basically created a situation where we can do short and long duration and short, long term. Most energy storage technologies are going after short term or long duration. We can do it all. We can do 10 hours, we can do 100 hours, we can do 1 hour. And that's because we won't ever ask the weight to move at a significantly different speed, but we will combine different wells in clusters to operate in different output scenarios. So you could have 10 wells operate perfectly simultaneously to be a 1 hour discharge. It takes about an hour to get from top to bottom. And then it takes about an hour to get from bottom to top. So you can recharge all that system in 1 hour, recharge, right? Not electrochemically. But then you could have all those wells, all 10 wells operate perfectly sequentially. And it would be effectively a 10-hour battery. And it can do anywhere in between. So that makes us extraordinarily unique. And we think that in the future, it's the most flexible energy storage technology that will win, because what the grid is going to need is not going to be discrete and arbitrary amounts of duration. It's going to be weather dependent, which is going to be variable. So one day the grid's going to need 50 hours. The next day it's going to need 212. And the next day it's going to need 91.7. It's going to be variable. So the technology that can match that is going to have an intrinsic advantage. This is just to give you some scale. So there are 284 gigawatt hours of energy storage capacity in the United States today. That's dominated by pumped hydro, but we're not building any more of those. So what we're talking about is converting upwards of 1 million idle wells. And that's sort of our North Star, our guiding principle, convert 1 million wells. There's another million or so odd wells in the rest of the world that could have a pretty important impact as well. We want to plug a lot of wells, right? This is a volume play. And we want to have a significant impact on the cleanup process. And that's why we made the company. We really just want to blow it out of the water. We want for way more wells to get cleaned up way faster and turned into energy storage much faster than they would have just simply been filled full of cement and buried. That's it. Happy to take questions, and thanks for this platform.
Fantastic, Kemp. Thank you very much. It is wonderful to hear about what certainly looks to be a win-win-win situation. So in a minute, I'll hand it back to you for a final word, but let's do the standard wind down. We thank you for joining us and for helping us share the stories of those who seek to improve their communities, locally, globally, and digitally. We are part of Rotary International, 1.4 million Rotarians and Rotaractors in tens of thousands of clubs around the world. Our club is both online and always available, so you can attend one of our meetings at any time by choosing the link on our homepage, which you can find at rotary.cool. In our meetings archive, you can find the full recordings, including the Q&A between the speakers and participating members and guests. If you are interested in joining Rotary, are a former Rotarian looking to get back into the organization, or simply interested in how you might make a difference in the lives of others, take a look at the Join page on our site or at rotary.org. You can also find these links in the podcast show notes. So with that, we appreciate that you're being part of this today. And as we like to do, we hand it back to our speaker for the final word. So Kemp, what would you like for people to be thinking about as they walk away from the recording?
Just know that what Renewell is building is the lowest cost, highest GHG abating, most flexible energy storage in the world.
Beautifully succinct. Great. Everyone, we will see you next week.